whether S on closed under addition. This is to say that if we have addition, if we have two matrices A and B in S on, so two diagonalizable matrices where the A plus B is also in S1 or not. And this has to be true for all A and B. So we know the answer is no. We have done that. For we know the set on diagonalizable matrix is not a subspace. To find a counterexample, we need to check that whether there exist two matrices A and B that are diagonalizable, but A plus B is not. So we search for example A and B. So we want A is diagonalizable. So just pick one diagonal matrix, say 1, 0, 0, 2. So this one is actually a diagonal matrix and therefore is diagonalizable. B is the 1B in S1. So B is diagonalizable. I don't know what value is this B, but we know a theorem saying the matrix here is a upper triangular matrix with two eigenvalues, upper triangular matrix. So the eigenvalues can be seen directly from the diagonal of the matrix, in our case A and C. And we want B to be in S1. We want B in S1. And we have a theorem saying that if the eigenvalues are distinct, then matrix is diagonalizable. And we call that if the matrix A, say n by n matrix, and A has n distinct eigenvalues, then A is diagonalizable. This question is very nice. So this one we want to be in S1. So to make it easy, just choose A and C are different. So we know that if A and C are different, we know for sure whatever matrix B is, it has to be diagonal. So in our case, we choose this so that A is different from C. Now, A and B are both in S1. And we want A plus B is not in S1. A plus B into the sum of two matrices and figure entries 1 plus A, 0 plus B, 0 plus 0, 2 plus C. We want this matrix is not diagonalizable. So not in S1. And to make it easy, choose this one to be same. If we choose to be something not diagonalizable. How about 0, 1, 0, 0? matrix for sure is not diagonalizable. Why do I know that? The two eigenvalues 0 multiplicity to matrices electrons. 0 is an eigenvalue of that matrix. Take this B. It has multiplicity 2. We know that the eigenvectors correspond to 0. Say V, the eigenvectors, so it has to be non-trivial. Eigenvectors corresponding to 0. V has to be in the null space of that matrix. 0, 1, 0, 0. So you see what you do, you solve the equation V1, V2, 0, 0 to find the eigenvectors. Usually if V is not, the eigenvalue is not 0, you do this of minus lambda. In our case, lambda is 0. So the matrix is this one. This is equivalent to 0 V1, 1 V2 is 0. So we know that V2 is 0 and V1 is free. However, we want eigenvectors, so it has to be non-trivial. V1 can be anything but not. V1 is not 0. So V1 is free and V1 any real number is equal to 0. The eigenspace corresponding to 0 is the space spanned by the vectors 1, 0. Those are the basics of the eigenspace. V1, 0, V1 times 1, 0. These vectors form the basics for the eigenspace. Span 1, 0. So although the eigenvectors must be non-trivial, the eigenspace will contain, always contains the 0 vectors. This is the eigenspace has dimension 1. This is not equal to the algebraic multiplicity of 0. So the geometric multiplicity of 0 is 1, algebraic multiplicity 2. This is to say that we did formally prove that this matrix is not diagonalizable. So it is not an S1. So we found example of A and B. So A and B, if you really want to see the explicit example, just try to find A and B. So in our case, if we have 1 plus A, 1 and 3 equals 0, 1, 2 and 3, B equal to 1, 0 equals 0, 2 plus C, 0. So we know that A is minus 1, P 1, C minus 2. So we have an explicit example of matrix B. So an explicit example of B is minus 1, 1, 0, A we have that here's an A and B. They are both diagonalizable. They are both elements of S1. But A plus B in our case 0, 1, 0, 0 is not in S1. Then we will conclude that S1 is not closed under addition, and therefore S1 is not a subspace of M by N. So if you really need to write down the form of proof, is enough to just give this example. We don't even need to explain why we construct the example. But here's one way of construction. There's multiple other way of construction. Here I choose the easiest way I just use an upper triangular matrix, so I don't need to compute the eigenvalues, and I just choose the example where the two eigenvalues are distinct. So for sure the matrix is diagonalizable. So the example where eigenvalues can be the same, but the matrix is still diagonalizable.